Alright, we're going to start talking about Chapter 8, which is right triangles. And the first lesson we're going to talk about is right triangle similarity. Now, right triangle similarity, just like the other triangle similarity theorems you had, bases itself off of angle, angle, or side, angle, side, or angle, side, angle. You remember those things. Well, today we're looking at one right triangle, triangle ABC, and it or ACB, and it has the altitude of CP. Well, you need to remember that an altitude is a line dropped from one of the angles of the triangle to the opposite side, and it's perpendicular. Now, when we have a right triangle with an altitude drawn to the hypotenuse, it makes three different similar triangles. Each one of these little triangles is similar to the other, and each one of these little triangles is similar to the whole triangle as well. So I went ahead and wrote that similarity statement for you. Triangle ACP is similar to CBP, which is also similar to the whole big one, ABC. And you'll notice that C and P are both the angles that are right, so they keep them together. And that A is similar to A when we're talking about the big triangle. If I'm talking about this little triangle to the big triangle, the A and the A stay together because they're congruent. And P and C are congruent because they're both right angles, so that's where that angle-angle similarity comes in. The same thing would be true if I look at the other two small ones. The B's are one pair of congruent angles, and the P and the C are another pair of congruent angles, so these two triangles are similar by angle-angle. And then these two, the same reason. You're going to need that information because if I were to say angle A is acute, name another acute angle, you would tell me angle B in the big triangle ABC, or you would tell me angle ACP in this little one because that's not the right angle. So just for some language points. Now, these two triangle similarities set up a couple of other pieces of information that we need to know in order to solve the rest of the problems in this assignment. But there's one other thing we've got to remember, and that's about a proportion. Do you remember solving the proportions? And we had a couple of words. We had extremes and mean. And the extremes were A and C, and if these guys were called the means, and that if these two were the same letter, it's called a geometric mean. It should be somewhere stored in the deep, dark secret of your brain. We're going to use that terminology in order to solve some ratios in this particular triangle, because there are a couple of corollaries. Remember, those are facts that come off of theorems that relate to the lengths of the sides of a right triangle when an altitude is taken to the hypotenuse. So I'm going to use everything in relationship to this picture. And you're going to see this picture over and over again in your assignment. And the letters are pretty standard. And what we're going to do is talk our way through it. So we know we have an altitude that's drawn to the hypotenuse. This altitude is the geometric mean between the two parts of the hypotenuse. Now, in order to know what that means, we've got to think about this geometric mean part up here. And so if the altitude is the geometric mean, then that means that this proportion is always true. X is to H as H is to Y. So I'm going to tell you what the geometry part was again, and that was that the altitude of a triangle is the geometric mean between the two segments of the hypotenuse. All right? So now the next corollary we have It tells us this crazy thing that an altitude to a hypotenuse intersects it so that the length of each leg is the geometric mean between the length of its adjacent side and part of the hypotenuse. Huh? I know, that's a lot. So here's the deal. Each leg is the geometric mean between the length of the hypotenuse and the side that is adjacent to it. Each leg is a geometric mean between the side of the hypotenuse that is adjacent to it and the length of the hypotenuse. Leg, geometric mean between the side adjacent to that leg and the hypotenuse. So that means we're going to have one other one. B is the geometric mean between what? The side adjacent to it and the entire hypotenuse. All right, so I'm going to have these three ratios that I'm going to use to do all of my assignments. All right, so on page 308 in your book, it gives you this picture. And question number 10 on page 308, 308 number 10, says that x is 9 and y is 25, and it wants you to find the missing lengths. Well, the missing lengths are A, B, C, and H. All right, well, C should be pretty easy. If x is 9 and y is 25, how much is C? That's right, 9 plus 25 is 34. Get your calculator. Use your calculator. It is your friend. Now, I want to find H, so I'm going to use this first formula. X is to y. X is to H as H is to Y. I'm going to substitute, 9 times 25 is 225. I'm going to take the square root of both sides, and H is 15. Okay, 2 parts down, 2 parts to go. Got to use my adjacent leg piece thing. So here's my ratio. X is to A as A is to C, because I've got to use the side to the leg as the leg to the hypotenuse. So 9 is to A as A is to 34. 9 times 34, I don't know what that is. 6. $306. I don't have a calculator on me. Square root of 306, is it a perfect square? I don't think so. I think it's going to wind up being like 3 on the square root of 34. You can change it to a decimal if you want to. All right, so now we've got to do y is to b as b is to c. Y is 25. We don't know what b is. So now you're going to do 25 times 34. I don't know what that is, but I do know this. You remember when we solved these radicals? I could take the square root of b squared and the square root of 25 times 34. And the square root of 25 is what? You're right, 5. Can I take the square root of 34? I cannot. So I can leave it just like this, and that answer is perfectly fine. All right, so now you have your assignment. Get on it.